This video is entitled Lines and Planes in Space. Now in the plane, we use slope as what determines the equation of the line based on the direction of the line. In space, it's more convenient to use vectors to determine the equation of the line, because you really don't have a concept with three axes here. Really, rise over run doesn't make sense, so that really wouldn't accomplish much. There's no such thing basically as a slope, unless you knew you were specifically on one of the three planes, xz, yz, or xz, yz, or xy. Well, anyway, with that being said, to come up with the equation of a line, we need to have an appropriate direction vector associated with that line. So if we know a direction vector and we know a point, we can then determine the equation of the line. So what they're showing you here, so let's say we have this vector v as ABC, and this vector PQ is also parallel to vector v, so it's essentially the same thing. So if we use the form to write this as if, as a vector, we would be taking, so x, y, z are arbitrary values of x, y, and z. This x1, y1, z1 is a fixed point. So you take x minus x1, y minus y1, and z minus z1. That would be equal to the vector ABC. And of course, in the line, keeps running on there, forever and ever, essentially. So the A, B, and C are called the direction numbers representing that vector. So it's all points through that Q where vector PQ parallel to V, and that means PQ is a scalar multiple of V. So now let's look at this. Here's how we define the PQ vector as x minus x1, y minus y1, and z equals minus z1. That's going to be equivalent. We're using t as a scalar here. And that would be parallel to AT, it would equal AT, BT, CT because of being parallel, which also is known as T times V. Now by equating these corresponding components, you can come up with, so for example, if you set x minus x1 to AT and then move the x1 over, you come up with this equation right here. X equals x1 plus AT. Same thing with the y. If you move the y1 over with the bt, you would have y equals y1 plus bt, and then you have z equals z1 ct. So technically the p can be any point on that line, whatever the value is for any point on that line, and then a, b, c represent the direction vector. And then that means by changing the values of t, you are creating all the various points on that line, obviously infinite points on that line. So anytime you use a new t, that's a new point on the line. They also have this form. I'm not as fond of a symmetric form, but we do need to take a look at it here. I like the parametric better. But parametric, what the symmetric form is doing, if you take each of these equations and solve for t, do a little algebra there, you can see that the first one would be x minus x1 divided by a, and then you would have y minus y1 divided by b, and then z minus z1 divided by c. And if t equals t equals t equals each of those, then they all equal each other. But sometimes you run into situations where if either A, B, or C is 0, what you would see is you would not see that particular component there. Obviously, you can't have divide by 0, so there would be nothing there. Yeah, we're going to see some problems that give it to us in this form, but so we do have to be aware of it. All right, let's take a look here. Find sets of parametric equations and symmetric equations of the line through the point parallel to the given vector or line if possible. All right, so here's your given point, -3, 0, 2. Here's your direction vector, 6j plus 3k. And which then, because there's no I component, so you can component form, you can write it as 0, 6, 3. And then therefore in parametric form, so your point would go first as your x1, y1, 0, z1. So it's -3, 0, and 2. And then your ABC, your direction vector numbers that go with the t, are 0, 6, and 3. And because there was a couple of zeros in there, I just kind of cleaned this up a little bit. I mean, nothing wrong with the way I wrote it there, but I kind of cleaned it up. And we have x equals -3, y equals 6t, and z equals 2t. And I happen to graph that line in Maple. And of course, x is always -3. Hard to tell from this first picture. Second picture is probably a better representation. You see as the line is heading that. Now this has the axis reversed. It's showing this as the negative side for x. It's rotated around. But you can see looking downward at it that the x is always -3. Harder to tell that from this picture. But then y and z coordinates would be changing, for each value of t, you would have a different y and z. Now in symmetric form, because y is, we have this 0 here. I'm sorry, the 0 for the a, not that 0. The 0 for the a, we would not have, the symmetric form would not contain x. It would only contain y and z. That's why I find that to be a bit limited. Whereas the parametric, you'll always have an x, y, and z. So basically it's just taking this equation, solving for t, which is y minus 0, which of course is just y, divided by 6. And then z minus 2 divided by 3. And there we have it. So here's a question I'm asking now. Is the point -3, 18, 11 on the line? Well, don't worry. We don't have to, graph this to find out. That's not it. All we have to do is, can we find a value for t that would create that point? So what you would do is come back up here, look at the parametric equations. Well, the x is always -3, so don't worry about that. But if you're trying to get, okay, if the y component, y value is 18, I need to know what value of t would make that equal to 18. Well, that's going to be 3, obviously, right? So then that means t is set at 3. So that means when you put 3 into this t to get the z component, that number would have to be whatever would be the z component. So if you put 3 in there, 2 plus 3 times 3 would equal 11, and that's what we have here is 11. So therefore, the answer is yes, because the same t, would generate that point. So that's how you would check. Kind of what I did right here. Yeah, there'll be some circumstances where what if we need to find a point on the line given the parametric equations. Well, that's really easy. Just pick any value of t. Now this is just a case of we had to use 3 because of that 18 right there to produce that point. But most people probably would just use, if you had to come up with a point on this line, it's just use 0. It's probably, well, actually we already have a point on the line. Excuse me. But let's say, pretend like we didn't have that point and we were just staring at the parametric equations. Put 0 in there, that would generate you a point on the line. That would probably be the easiest thing to do. But mathematically, you can pick any value for t. That would work. Now, let's talk about finding a parametric equation on the line between 2 points. And we can do that. So you're either going to have a point and a direction vector, and sort of like in the plane where you have a point and a slope, or in this case, which this is like the plane, you can have 2 points to determine it. Well, if you have 2 points, the direction vector will be the vector between the 2 points. That's what we can calculate the direction vector. So that means when you don't have the direction vector given to you, you have enough information to get it, because you'd have to have 2 points provided. So we would take, I'll go from P to Q. You could go from Q to P. That's not critical. But I'll go from P to Q, either direction. 1 minus 2 is negative 1. 4 minus 0 is 4. Negative 3 minus 2 is negative 5. And you can use either point to generate this line. I mean, yes, the answers would look slightly different, but what happens is if you use either point, that just means different numbers for t will generate the exact same points on that line. So, for example, if you reverse it, say, so if t, t equals 2, and that yields a point, and you'd reverse this, that means there will be a different t that will yield that same point on the line. So you're going to get every point on the line represented, so it doesn't matter what order you go here. But I just use 2, 0, 2 as the initial point. So here's my 2, here's my 0, here's my 2. And then negative 1, 4, negative 5. So you have negative t, 4t, and negative 5t. So I left the 0 there, but obviously you can just write that as y equals 4t. And I just happen to graph it for the heck of it. There's that line in space right there. Okie doke. All right, now we're trying to find, here we got a point, and we have them in symmetric form. So anytime you would see something like this, because you have to make it a fraction to get your A, B, and C off the bottom. So I have to put that over 1, even though they didn't write it that way. So that would be divided by 1, because that's going to be your component for the direction vector. So those denominator values are your direction vector, 3, negative 2, and 1, right there. And your point's going to be, well, there's your point right there. Negative 3, 5, 4. So you can just go negative 3 right here, plus 3t from the direction vector. 5 minus 2t, and then 4 plus t. And that will be your parametric equations of the line, starting with that symmetric form. So let's see what we have here. Okay. Planes in space. Alrighty, let's see what it looks. So there's a nice little pinkish, purplish looking plane right there. A nice graph of one, so most people would be aware of what a plane is. Now the things that you need for a plane in space, the two things that we need are, we need a point, any point on the plane, and we actually need a normal vector, a 90-degree vector sticking out from where that plane would be. That seems kind of strange, but it's absolutely true. So we're not looking for parallel here. This time it's got to be a normal vector. So if you're given, now they're still using the same ABC as was used before for vector V being the parallel vector ABC. Don't let that confuse you. Most people do okay with that. So, but anyway, here's the standard form of the equation of the plane. So A, B, and C are your normal vector, and then you have x minus x1, y minus y1, z minus z1. That's called standard form. And you can expand it out and distribute. So if you were looking at a problem that on a multiple choice type quiz or test or something, maybe the answer was written in this general form, but that's just a matter of algebraically distributing out the numbers. It's not a separate thing you come up with here, so it's not that big of a deal. Just to distribute, combine all the terms together. and then we have the general form of the equation. In a previous video, this idea was mentioned here, that basically they're just used in different concepts. Normal, orthogonal, and perpendicular are kind of all mean the same thing. Like we talk about a vector being normal to a plane, but then we talk about vectors being orthogonal to each other. It's just kind of interchanging the same idea of perpendicular 90 degrees. So don't let those terms get you confused. So here we go. The plane passes through the point -4, 5, 2, and has a normal vector of 3, 2, -5. Find the equation of the plane in standard form. And really easy. So 3, 2, and 5 are your coefficients in front of the parentheses. So we have -4, x minus a -4 is x plus 4, y minus 5, z minus 2 equals 0. Now here's a question. Is the point -3, 8, 1 on the plane? Well, this is kind of a rule. You don't need to use any fancy ideas for this. Basically, the idea with any kind of equation, if you plug some numbers in and it equals what's on the right side, like you can do the same thing for a line in the plane, which is easy. But what I'm saying is, any point, any xyz point that satisfies this equation means it was on the plane. In other words, if I plug the x, y, and z in here and I get 0, it equals that right side, then yes, it's on the graph. If I get anything other than 0, the answer is no. So obviously we know -4, 5, and 2 is on the plane, and that means if you put that in there, if you plug, you would get 0. Well, so there's nothing fancy here for this mathematically other than just plugging the numbers in and see if it equals 0. I put -3 for x, I put 8 for y, I put 1 for z, and 3 plus 6 plus 5. I didn't finish that, but obviously that was not going to equal 0. So no, then that point is for sure not on the plane. And we'll be looking at later where we're having to, if we have an equation of a plane, can we come up with a point on the plane? So we'll talk about that, but that's pretty easy. Now this is interesting. A line passes through the point -4, 5, 2, and it's perpendicular to the plane given by -x plus 2y plus z equals 5. Find a set of parametric equations for the line. So I kind of just sketched a little picture here. A little bit better one there in Maple going down there. But anyway. All right, so here's showing you that the line is perpendicular to the plane. Therefore, that line is parallel to the normal vector of the plane because they're both perpendicular to the plane. So that's good. So that means the direction numbers for that normal vector are going to be the same direction numbers for the line because, like I said, the whole key to this is that line is running perpendicular to the plane. So we can use the n. And the n, remember, will be the coefficient. Even though that's expanded out, don't worry about it. The normal vector to the plane is the direction vector of the line and will be the coefficients of this equation right here. So it's -1, 2, and 1. So that's your direction vector. And then now you have the point given, which is -4, 5, and 2. And so now it's really easy. So now we go back to the parametric equation. So we have -4, 5, and 2. And then the direction vector then is -1, so it's -t. And then 2 makes it plus 2t. And then 1 makes it plus t. And there we go. Now there's another part to this, I believe. Let's see. Yeah, for the last problem, can we find the point of intersection between the line and that plane? Yeah, in other words, so how do I know? Could I tell real quick? Is that point that's given right here, is it on that plane or is it not on that plane? Or is it just somewhere else? Obviously it didn't have to be on that plane. Well, the fact that they're asking us to find the point probably tells you it's not. But once again, going back to the idea from the last problem is, if you plug in -4, 5, and 2 into this equation right here, you will see that it does not equal 5, so the point's not on that plane. So now what we're trying to do is we are trying to find the point that is. The point that would be on the line and intersecting with the plane. In other words, where is that point hitting the plane? Kind of like if you look at the maple drawing there, see where I have that drawn, that arrow there? We're finding that point of intersection. Now let's see. So, the points on the line move based on whatever the value of t is. That's how we determine them. So let's say if we take here's the equation of the plane right here. We have that. And now, suppose I use the x, y, and z that represent the parametric equations for the line in terms of t. So if I substitute each of those in there from right back up here, scroll back up there for a second. There they are right there in pink. If I substitute each of those in there for x, y, and z, what that's going to do, it's going to find me the value t where that point is hitting that plane. Sorry, where the line's hitting the plane, but yeah, the point where the line hits the plane. That will tell you the t. Now that won't be the final answer. That value of t, though, once you plug it into the parametric equations of the line, then that will determine the point that fits. So it's kind of tricky to see what to do, but once you see what to do, it's not very difficult. So you put these three parametric terms in there, and you just kind of do all the algebra. That's easy enough. And you get a -11/6. So when t equals -11/6, that means the point is where the line's hitting the plane, is right there. So all I do, like I was saying, is I take the parametric equation of the line and I substitute a -11/6 for all the values of t, and I get this coordinate right here. So -13/6, 4/3, 1/6. Now, one thing you could do, I thought I had done this, but I guess I didn't, but I'll mention it verbally. Obviously, it's hard to tell that that's the right answer from this picture, but it is. If you take, because we pretty much then derive the point from the so this point on the line we know is a valid point on the line. But if you wanted to just absolutely verify it's right, is if you substitute that point into the equation for the plane, it needs to be true. And I've done it before, but I guess I didn't save it written out. But I've put in these three fractions on this left side, and you can check it yourself. Go right ahead. And it does equal 5. So that sort of gives you a little more reinforcement that we have the right answer. Now this is an interesting problem. Suppose that we are given 3 points. So instead of giving a point and a normal vector, we are given 3 points. And this is unlike the equation on the line. We have to have 3 points for this, not just 2. The reason why is because we don't. So we have 3 points, which is 2 more points than we actually need. But the issue is, how do we get the normal vector? Alrighty. So what I'm going to do is create 2 vectors between a couple of those points. Any 2 makes no difference. Now on the section on the cross product, we learned something very valuable there, that when you take the cross product of 2 vectors in a plane, that will generate a vector that is orthogonal to that plane. So to get our normal vector, then we take any 2 vectors combined between those 2 points and do the cross product here, and then that will give you your normal vector. And the reason why it doesn't matter is we don't care if that normal vector goes positive, through, up, or down, as long as it's 90 degrees. In fact, I'll show you here. and because the length of it doesn't matter. Now, I didn't show the work for the cross product there, so you can go back and look at the formula and work that out. So I labeled these A, B, and B, C, and I crossed them, and the order didn't matter. 5, 10, -5, and in fact, I just reduced it to 1, 2, or use. I'm not saying they're equal vectors, but I'm using a multiple of it, 1, 2, -1. Yes, because it's not the same vector, but it's parallel to it. It's just a different length. It's a fifth of it, so it would still be normal to the plane. In fact, you could check. One thing you could do if you wanted to is you could take either of these vectors and do a dot product with both those vectors to make sure they equal 0. If you wanted to, that's optional. Then you'd know you're okay. So that's why I did this, just because. Well, one reason is that when these answers are written in sort of not the standard form, but the general form, they're usually written in lowest terms, like if it reduces. So since this reduced by 5, I went ahead and reduced it now, because if not, I may need it to, if I was answering a multiple choice question, I would need to reduce it at the end. So I'm just choosing to reduce it now. But like I said, it's still orthogonal, so it works. Let's see what we have here. So I'm going to use any of the points. Any of the points will work. So I just chose to use A here, but anyone, I can't stress enough, any one of them will work. So here's, I did, even though I said or use this, I still used 5, 10, -5, but I reduced it at the end. So I probably should have just used the 1, 2, -1. But anyway, that's all right. Let's just look at the setup. So it's 5 times x minus 3 plus 10 times y plus 1 minus 5 times z minus 2. And then, that's okay in standard form. But just in case we need a general form, I distributed and expanded and got a 5 here. Now, sometimes in general form, they'll leave it set equal to 0, or they'll move the number to the other side, which is what we had right back up here. See that plane right there? The number was on the other side. So, but that's not difficult. So I reduced it because you would probably see it reduced if we did it that way. Now, one thing to keep in mind, you might get slightly different values depending on how you, when I say different, they still have to have the same common thing I'm about to say here. It's got to be a multiple of each other. So let's say you did this problem and you got to this step, and let's say you had -x minus 2y plus z minus 1 equals 0, and you're thinking, oh no, I messed this up. All the signs are the opposite. No problem, because if you took this equation and you multiplied both sides by -1, 0 would still stay 0, and then it would match this answer exactly. Or vice versa. Maybe I would have to take my answer and match it to the other one. But then I could just see that since everything is off by -1, then that would be right. I would know it was correct. It would be off by a common multiple of -1. Now, this is just if you wanted to. I was just checking to make sure that the other 2 points, because obviously in the original problem it said all 3 of those points were in the same plane. Therefore, all 3 of them must satisfy the equation of that plane. So I'm taking this equation right here, the reduced form, and I'm plugging in both those points. And I got 0 for the first one, so that's correct, because it equals 0 here. Obviously, we had a number on the other side. We'd be looking for that number. And this one equals 0, so that makes me feel really good about my answer. All 3 points are on there, so that's probably a good. And there's a little graph of that plane. Okay, let's see what we got here. Find the equation of the plane passing through the point perpendicular to the given vector or line. Kind of same thing as that problem we did earlier. So if the plane is perpendicular to the line, that means whatever direction the line is going is our normal vector. So you see I had to put this, it's in symmetric form, so I had to put this over 1 again because there was no denominator. So 4, 1, -3 is your direction vector for your line, but because it's perpendicular, it's also the normal vector for the plane. So those are your coefficients, 4, 1, -3. And this one's not too bad. So there's 4, 1, -3. Here's your point, 3, 2, 2, 3, 2, 2. So if it's in this form, if it's in standard form here in pink, we could stop right there. Or if we had to expand it out and distribute it, we can come up with this in general form if we needed to. All right, now we have one that says a plane passes through the point 1, 2, 3 and is parallel to the YZ plane. Parallel to the YZ plane. Kind of interesting. Well, any vector, the standard, I'm using the standard unit vector I here because that's good enough. But basically, let's see if I can just draw this here. Maybe I can go find another picture of the, better picture of the coordinate system. Yeah, it's a little better. You see, so here's the YZ plane right along here. So anything going in the X direction would be perpendicular normal to the YZ plane. So basically, for example, if you're trying to find a normal vector to the XY plane, it would be anything going up or down the Z axis. If it was the XZ plane this way, anything going up or down the Y axis would be normal. And then in this case, for our problem, it's the YZ. And so anything going in the Z direction. For example, anything on the YZ plane is going to have a 0 coordinate for the X value. So you could pick any point on here. It's just going to be 0. And if I put 0, 2, 3, for example, it would be easy to come up with a normal vector by putting in, I'll just use any X goes here. And I'll skip the commas here this time. It's too hard to draw this. X, 0, 0. So if you look at that, you can see that dot product would be 0, wouldn't it? Because no matter what X is, 0, that would be 0 because of here, and then 0, 2, 0, 3, so it would be 0. I'm just using the standard unit vector I, 1, 0, 0, but my point is that you know, if you used 2, 0, 0 or 6, 0, 0, -5, 0, 0, it would all work. So I'm using 1, 0, 0 right here, 1, 0, 0. And you have the point 1, 2, 3, so it's x minus 1, y minus 2, 0 minus 3. So basically you're left with x minus 1 equals 0, so it turns into x equals 1. And I have this one graphed down here in Maple, so you see the picture is that x equals 1, that in 3 dimensions, that is a plane. You know, any x equals, y equals, or z equals a number is still a plane. And that plane, x equals 1, would absolutely be parallel to the YZ plane, and it would just be 1 unit away from it. Right there, 1 unit away from the YZ plane. So in other words, anywhere on that plane, x equals 1, and then of course y and z can vary or whatever. So here's another one about finding the point of intersection again that we did earlier. So we'll take a look at another one of these. So I took the symmetric form here and converted it to parametric to be able to, I needed to be able to substitute like I did. So this, you know, it's 4t right there. So x equals, basically x minus 1 equals 4t. So x equals 1 plus 4t. And the middle one's y equals 2t. Because, you know, it's y minus 0 in the numerator. And then z equals 3 plus 6t. So yeah, because basically, you know, your x1, y1, z1 are up here, and then your a, b, c are down there, and they're easy to convert to parametric. Now this equation just doesn't happen to have a z, so we'll actually ignore it. So I'll substitute the x, 1 plus 4t right there, and the y is 2t right here. And solve for t, I get negative 1/2, so that's going to be where they intersect. So all I have to do is take my parametric equations right here, put in negative 1/2 for each one of those, I get negative 1, negative 1, 0. So that's the point where the line intersects the plane. And you see you put in negative 1 right here and right here. It's easy to see that does equal negative 5. So that's checks. So we solved it for the line, and now that also checks with the plane. All right, well, looks like I did this again. Oh, this asking, does the line lie in the plane? So that's a little bit different. Meaning, you know, is the line kind of riding along with the plane? Well, let's take care of the usual business here. So we've done this a couple times, so I'll kind of go through this a little quicker. So these were given. I'll change the colors of these to make it look like they were. Looks like, there we go. All right, so here's the plane. Here's the parametric equations of the line. So once again, we substitute the x, y, and z in here into the plane. Solve this, and we get t equals 2. So you put 2 in there. And you'll get 5, 2, 13. As the point where they intersect. Now, the line is not on the plane since the line intersects the plane only once. So if it were, you'd be looking for some sort of answer where you've got infinite possibilities. I think I did one down here. Yeah, you'll see one coming up to be able to see, you know, how you would know that it would. So think about it, because obviously if the line is on the plane, there's going to be infinite possible points of intersection. But if we come up like we did here with only one unique solution, that means the line is only cutting through that plane once. And I'm assuming these instructions are the same here. Now this one, I'll kind of skip the preliminaries and come down here. Same process, substitute in there. Now, when you lose the t's, here's what happens. You have negative 1 equals 10, which is obviously a contradiction. That means there's no value of t where the line hits the plane. So what does that tell you? That means that the line is not ever hitting the plane. It is parallel to that plane, because it'll never touch. All right, and then now let's look at the solution where the one where the line is on the plane. And I also I don't think this was necessary, but I did take the normal vector for the plane and I dotted it with the direction vector for the line. So there they got 0. Therefore, the normal vector of the plane is perpendicular to the direction vector of the line. That means the direction vector of the line is running alongside the plane. In this case, parallel. It could run on top of it and still be the same thing, but I don't think that was absolutely necessary. Once we could not solve for t, that guaranteed we had that the line was never touching the plane. It had to be parallel. So here's another one, same process. We substitute the values in the parametric into the plane, and we have a situation now. The t's cancel just like the last one, and we have this as an identity. That's kind of like if you could do it back in algebra. That's how you could, if you were testing lines and stuff, you could see, in other words, if you're solving it, you came up with one equation of a line is exactly the same as the other equation of the line. If you were doing like substitution or elimination, and you got 0 equals 0 or 12 equals 12, that means they were the same line, they weren't separate lines. But if you got a contradiction like 0 equals 6, that meant they were parallel. So sort of working like that here. So that means any value of t will solve that equation. So therefore, I just showed a couple of examples. I used 2, I used 5. That would be the value for the line, but it's also on the plane. So therefore, everything that's on the line is on the plane. That means the line has to be on the plane. All right, how about angle between two planes? Very similar to finding the angle between two vectors, because to find the angle between two planes, you're finding the angle between their normal vectors. If you think about it, the normal vectors, these two planes, they're both going to be 90 degrees away from, perpendicular to the plane. So it's like shifting the planes over 90 degrees, and it's still going to be the same angle. So the angle between those normal vectors will be, so this is correct here. That theta between there is the same as this theta. Now, so that's what we do. Now, one exception, there is an absolute value in this numerator, because whenever we were doing vectors, it was finding the smallest angle, but we could have absolutely had something that was more than 90 degrees, like this. You just would not have it being more than 180. So you could have that, but not this with planes, because with planes you'll always have an angle there. It's either 90 or less than 90. So, like, imagine if this did, if the plane kept going through like that. So this formula is not going to automatically, it's going to measure it based on the smallest angle, which is this. So that's so in other words, it would not measure it as anywhere between 0 and 180. It's only between 0 and 90, because this will be the absolute value on top. Of course, then theta will be the cosine inverse of that. So it's actually quite easy then once we know this, so real easy. And these are good problems, because they're kind of testing out. We did this before, not with planes. We did this with lines, or with vectors, excuse me, not lines, but vectors. Testing whether they were parallel, orthogonal, or neither. Meaning if they're neither, then you'll find the angle between the two. I mean, if they're orthogonal, there's no point in finding the angle, because that's automatically 90 degrees. Now, what you want to kind of look for on these, at least is the way I like to do this, is I look to see if the direction vectors for the plane. If the direction vectors of the plane vectors, if they're a multiple of each other, you're going to have parallel. Now, one exception to that, which I don't think they're taking care of here, mentioning here, because there could be no answer to this, because the planes could overlap and be the same plane. For example, if one equation is the complete multiple of another equation, just like they are with lines, it's really the same plane. It's not two different planes. But I think they took care to make sure that wasn't the case here. So if your direction vectors, the normal vectors, are parallel, that means the planes are parallel. If they normal to each other by taking the dot product and equaling 0, then you have orthogonal planes. This is number 58, so I'm labeling here's the, so the first normal vector is 3, 1, -4. The second one will be -9, -3, and 12. So I kind of looked at that, checked for a multiple, and yeah, I could kind of eyeball that. Obviously, you don't have to do it in your head. You can write it out if you need to. But you can see that you take each term over here on the right vector, you divide it by the one on the left, you're going to get a ratio of -3 for all of them. Therefore, the second normal vector is -3 times the first one. So they would be parallel planes. Let's look at 62. It's going to be 2, there's no y, so it's 2, 0, -1. And then 4, 1, 1, 8 for the bottom one. Now you can quickly see that they're not parallel. Well, obviously you can't have 1 divided by 0, so they're not parallel. So now we'll check for orthogonal. In other words, just do the dot product between the two vectors. And I got 0 as the dot product, so that makes that answer orthogonal. So we're done with that problem. Now number 60. We have 3, 2, -1, and we have 1, -4, 2. And they're not parallel, there's no multiple. Then if you do the dot product, we get -7, so therefore that means it's not orthogonal. So the answer is neither, but now that it's neither, we can actually find the angle between the two planes. And that n1 dot n2 comes in handy, the dot product, because we actually, we need that for our angle formula. Got away from me here, let's see. So we need the magnitudes of each of those vectors, which are easy enough to calculate. You get square root of 14, square root of 21. Now, like I said, a few minutes ago, when we looked at this formula versus the angle between two vectors, we have to take the absolute value of that numerator. So the numerators always will be positive. So it's 7. But notice how I put the two numbers together under the same square root. You got to be careful with that. So I did this correctly, and I've got make sure you're in degree mode, because this answer will usually be asked in degree mode. I don't know, somebody might ask it in radian mode. I'm just saying, usually we're kind of looking for degrees here. At least I know I am. So I said about 65.9. Obviously, whatever rounding is required, or there's no automatic requirement. You have to be told. So I graphed the two planes, and there you go. I'm kind of just sort of drawing a little sketch there, and I also did it down here too. So roughly that's 65.9 degrees between those two, like that. Now, let's find the distance between a point Q and a plane. So what we're trying to do is we're taking some point Q that's not on your plane, and we're trying to find this shortest distance, the perpendicular distance. So it's not just any distance to the plane, it's the shortest distance to the plane. And of course, the point Q is not on the plane, because if the point Q was on the plane, then the distance would obviously be 0. So what we need to do is, the point we're given is Q in a problem, and we're going to have to find a point P on the plane, which that's easy enough to do, and I'll show you here in a minute. And let's see, and n is the normal vector for the plane. So what we have to do is we come up, so once we find that point P, we combine it with Q, and we form a vector PQ. This would actually work also if it was vector QP. So it doesn't make that much difference which order it is that you form the vector between the points. But just form that vector, and then we're going to dot product it with the normal vector for the plane over the magnitude of the normal vector of the plane, but we have an absolute value here in the numerator, because sometimes that dot product may be negative, and the absolute value protects it and makes it positive, because obviously if we are finding distance, then the answer is going to be positive. So let's take a look here. Okay. So this problem, so the point given is Q, 1, 3, negative 1. And here's our equation of the plane, 3x minus 4y plus 5 equals 6. So all we have to do is find any point on the plane. That means any x, y, z that would make this equation equal 6. Anything. Well, the good news is we don't have to sit here and just do, trial and error, plugging in numbers till it works. We can actually find a point real easily. And what I like to do is find an intercept point where if I zero out two of the values and solve for the other, then you have it. In other words, those coordinates you zero out would be then 0. So like this one, I kind of look at it to try to avoid fractions if possible, although if I have a fraction, it's not the end of the world. But I would look at this immediately and go, hey, if I let y be 0 and I let z be 0, I would have the equation 3x equals 6, and then that means x would equal 2, which is what I did right down here. And then I got 2, 0, 0 as a valid point that's on that plane. But like I said, there's infinite values you can get that are on that plane. So any point will solve that. So that's what I usually do. I just zero out two of the variables. Or if I see something else that just happens to look right, I'll do that. So let's get the PQ vector. Now I'll go ahead and make sure, even though I said either order didn't matter, and I still stand by that, I'm going to still make sure I do it as PQ vector, so it'll be Q minus P. 1 minus 2 will be negative 1. 3 minus 0 will be 3. Negative 1 minus 0 would be negative 1. So that's your PQ vector. Now I went ahead and find the magnitude of the normal vector, 3, negative 4, 5, and I get the square root of 50. We've seen how to do magnitude before, but that'd be real easy because you'd square the 9 plus 16 plus 25 is 50. So I take that PQ vector we found right here. I'm going to dot product it with that normal vector of the plane n, and I get negative 20. So that means the distance will be the absolute value of negative 20 divided by square root of 50, and 20 divided by square root of 50, which is perfectly acceptable answer. But I did show, reducing it, what it would look like. But that's, I don't know, that's wouldn't be mandatory with me, but I can't speak for all instructors, obviously. And certainly if this was a multiple choice type question, you could check the decimal values in the calculator. So let's say that if this was a 2 root 2 was one of the answers, well, you could take a calculator and take 20 divided by square root of 50, and then you would see it was equivalent to square root of 2. But I just broke it down into 5 root 2, 20 over 2 is 4. I rationalize the denominator, which means I'll have 4 over 2, and that gives me 2 root 2. But that's, just want to show you that. That's not critical. But 20 over root 50 is the accurate distance from that point to that plane. Now here, I'm showing you, suppose I used a different point P. So I came up with, I don't know why, I just came up with this, put in 1, put in negative 1, worked out to be 5. So anyway, 5, 1, negative 1 can also be a point that we use on that plane. So the PQ vector, just do each Q, there's the Q, so this is the P right here. So Q minus P, 1 minus 5 is negative 4, 3 minus 1 is 2, negative 1 minus negative 1 is 0. So if we dot n with PQ, and it's still it's 3. The coefficients negative 3, negative 4, and 5. So 3 times negative 4 is negative 12. Negative 4 times 2 is negative 8. And then 5 times 0 is 0. We get negative 20. So then you would still have negative 20 over the square root of 50, so it would be the same answer. Now here's a little maple shot there, a graph of it, where I put in the equation of the plane, and then that big ball represents the point. So then we're saying that this distance is here to here is 20 divided by square root of 50, which is 2 root 2, which is roughly around 2.8. Now that looks reasonable. Now it's hard to tell, exactly from that picture, but I could look at that picture and at least I could see that, if I'd have come up with a distance that was equivalent to about 15 or something, I would have known that something was wrong, either my graph or the calculation, but that certainly looks reasonable, 2 square root of 2 for that distance. And you can actually use this same formula to find the distance between the point and the plane. So one thing, if they're parallel planes, so it's going to find the shortest distance between the two. There's no doubt that our our normal vectors are going to be either they're going to be exactly the same, or one of them is going to be a multiple of each other, guaranteeing that they're parallel. Now here's the formula. A, B, C. We'll talk about the D thing here in a minute. This sort of means if you're in this form right here. So what we have to do then when working with this is you have to, if this constant here is on the right side, you have to set this equal to 0 and move it to the other side. We have to do that. Now what you want to do to make this work is you use a point from one plane. So we're actually finding a point on one plane and then finding its distance to the other plane. So the second plane will be the one we treat as the plane, and one plane we're only getting a point from it. I'm not sure if I'm saying that very well or not, but let's see if I've got, did I have to graph this? Yeah, so let's just say, I'm not sure this is the right way of it. Let me come down. So in other words, all I would have done from one of these planes is just got the point from it, and then we're at that point we're measuring the distance from that red point to the red plane, like that. Hopefully that helped my rambling there a little bit. And it doesn't matter which one's which, you just do either one of them. So what I did here was I took the top equation and let it, I just chose to use that one as the one I was going to find the point off of. And that means the other one's going to be the one that's treated as the plane. So put in 0 and 0 here, you get 2x equals 2. So that makes it easy. 1, 0, 0 is my point that I'm using from the top plane. And the other one will be the plane. So to match this formula right here, I've got to use I've got to move that D over, so that has to be negative 27 equals 0. So we're going to use that equation right up here, and then of course divided by the magnitude of that same normal vector using that point. So what we do, so to find the magnitude, I pulled a 2 out of there. I didn't have to, but I just did for the heck of it. We've learned that before with magnitudes. I pulled out a scalar multiple. So the magnitude is 2 times the magnitude of 2 times 3, 2 squared, 3 squared, negative 4 squared, 4, 9, 16. So that becomes 2 root 29 on the bottom. And then what you do in that numerator up here is you use this equation right here, the one that you're calling the plane, right there, and the x0, y0, z0 is the point right here that we found from the other plane. So we plug that into here. So there you see I have it written right here, and I have 1, 0, 0 plugged in there, of course absolute value, and that turned out being 23. So it's 23 over 2 times the square root of 29, or that would have been the square root of 116 if you had not reversed it. So I'll just do a rough estimate in my head, but so square root of 29 is going to be somewhere between 5 and 6. I'll just say like 5.5, which is 11. So 23 over 11 means a little bit more than 2. So that distance right there should be a little bit more than 2. All right. And next part, I just use the other formula. All right. Where'd it go? Here we go. So I found the Q, and then I let P be a point from the other plane, and then it did the PQ and dotted it with the N, and essentially I came up with the same answer. So you could do it that way too. Both formulas work for this problem. Mainly because they're parallel planes, of course, that's the reason. Distance between two parallel planes, same thing. I chose the bottom equation to be my. I'm always kind of looking to see whichever one I can maybe not have a fraction if possible. Not that I'm afraid of fractions or anything, but it's a little easier. So this one I looked at and saw, hey, if I let those two be 0, I'd have 9z equals 18. So 0, 0, 2 would be my point right there. So I'm using 0, 0, 2, then which means I'm using the top one as the plane equation right here. Now I got to move the 7 over to make it -7. So it's 4 times 0 minus 4 times 0 plus 9 times 2 minus that 7. Absolute value of that's going to give you 11. And then on the bottom, then the magnitude of that normal vector right here is going to give you square root of 113. So 11 divided by square root of 113 would be the distance between those two planes. Now, here's the formula distance between a point P and a line in space. Alrighty. So same thing, we're going to have a point given to us, that's going to be Q. We're going to have to find a point P, any point P on that line. That will be easy. We just did it for planes, now we'll do it for lines. We'll create the PQ vector, and then U is the direction vector for the line. So we do PQ, and we do a cross product with U. Take the magnitude of that because, unlike the other formula was a dot product, so we just use absolute value to make sure it's positive. Magnitude is always going to be positive, so no trouble. So since the numerator results of a cross product is a vector, the magnitude of it will make it a scalar, and then of course the denominator will be a scalar because it's a magnitude. So we have a scalar answer that will automatically be positive. Let's take a look at this. Here's the point. That'll be Q. Here's the line. And I mentioned earlier that we're going to have to, come up with points on a line when we're coming up with parametric equations, and here it is. So super, super easy. So you have this equation, just pick any value for t. Use the same value of t all the way across. Like I said, 0 is probably the easiest thing to do, but you want to use something different, maybe your favorite number is 3 or something, go right ahead. But if I put 0 in here, I'll have 0, and then 0 minus 3 will be -3, and 0 plus 2 will be 2. So I'm just choosing the point 0, -3, 2. as one of my points on that line. But like I said, you can get something totally different. It's still going to work. So that means so the PQ vector then would be Q minus P, but the other order. Same thing with the equation of the plane, is that PQ or QP doesn't make a difference, but if I'm labeling PQ, I should do it the right way, obviously. So, but you could have reversed it and it wouldn't have mattered. So PQ, 1 minus 0 will be 1. -2 minus -3 is 1. And then 4 minus 2 will be 2. So you have 1, 1, 2. And then we have the direction vector for the line is the coefficients of t. Remember, those are your ABC. Those are your coefficients on the line. So 2, 1t makes 1, and 2. So 2, 1, 2 is vector u. In another section way back when we talked about unit vectors, I'd mentioned this, that, obviously you never assume that even though it's defined using u, that a vector named u is automatically a unit vector, and this is a good example of that. So it's not a reserved name. So the fact this formula had a u, that didn't mean it was a unit vector. So we have 2, 1, 2. And I need the magnitude of u, which happens to work out to be 3. And PQ cross U, either order. Now, I'm not, okay, so I'm not going to go through the steps, the cross products. I've shown that in another video. But here I've attached the formula for it here so you can see, and you can run back through it yourself if you want to for practice. Not a bad idea. But I got 0, 2, -1, which means I'll need the magnitude of that, which means it'll be 4 plus 1 is 5, so it's the square root of 5. So the numerator will be the square root of 5. The denominator will be this 3. So I have the square root of 5 over 3. Okay. And there you go. There's that distance. Hoping I graphed. Yeah, okay, I've got one graphed right here for this next example, which was number 92. Here was this one. So same thing. You got a Q. You got the parametric equations. And for no reason other than I felt like it, I chose 1 here for my t as 0. But any choice of t is fine. I just chose 1. What the heck? So x is fixed at 3, so it doesn't matter. And then 1 plus 3 times 1 is 4. But I promise you, if you went back and used 0, it'll be correct. And then 1 plus 1 will be 2. So my point P is 3, 4, 2. So if you calculate the PQ vector, you'll get 1, -5, and 3. And the direction vector of u is there's no t here, so that component's 0. 3t, so it's 3. And 1t will be 1. So you have the PQ and you have the u. So there's the magnitude of u, which we need is the square root of 10. I have to do the cross product, which the formula is on the other page. I'll skip the formality on that. But here's the cross product, which will result in -14, -1, and 3. So the magnitude of that cross product equals the square root of 196 plus 1 plus 9, square root of 206. So the distance between the point and that line will be the square root of 206 divided by square root of 10. So roughly the square root of 20, about 4.5 or so, 4.5. And there we go. Look at the line right there. There's the point. Hey, look, there's 4 down there on that axis. So a little more than that. So there it is. About 4 point something would be that distance going from that line to that point. And that concludes the video for lines and planes in space.